All right, back to the top of this slide, I want to address a few more of the things that I mentioned here. In the last video, we saw this method of initial rates, and now I just want to briefly talk about the isolation method and then see how the rate law expressions tell us or depend on reaction mechanisms. Okay, so here's the so-called isolation method. And again, we've got a rate law expression. And we have an unknown I and an unknown J right up there. Now the way the isolation method works is you make the concentration of A very large. And by doing that, the effect you're going to have is the concentration of A will be approximately constant. Because if it's got a very large concentration, then it's not going to run out very quickly in your reaction. So therefore, we're going to be able to write a rate law just like we did before. But since these two things are approximately constant, we can just assign it a new effective rate constant, K prime, okay? So K prime equals K times the concentration of A to the ith power, again, approximately constant, and our new rate law is just going to equal K prime concentration of B to the J power, like so. So then all you need to do is, at this point, take one measurement of the rate and one measurement of the concentration of B, and you're able to create a linear system of equations. If we take the natural log of both sides, then we will get the natural log of K prime, and this is going to be plus J times the log of B. So as you can see, this is a y equals mx plus b type equation. And so here's just another method to find the unknown J and the unknown K prime. Next, I'd like us to consider the effect of reaction mechanisms on the rate law. So we're going to have another hypothetical reaction. Let's say that A reacts with B, reacts with C, and this forms products. And let's say that this reaction has the following mechanism. First, A combines with B to form a complex, AB, and let's say that this step of the reaction mechanism is slow. Then the second step, this complex of A and B reacts with C, and that forms the products. And let's just say, for the sake of argument, that this step is fast. I can tell, based on this mechanism, what the rate law is going to be. The rate law is going to be a rate constant, concentration of A, concentration of B. And that's because the rate law always depends on the slowest step. And since the stoichiometric coefficients are 1, this rate law is first order for both of those reactants. And because the second step is so fast, the concentration of C will not determine the rate of the reaction. So this is just an example that shows how the rate law depends on the slowest step of the reaction mechanism. So what's the purpose of the rate law? The reason why we like to know the rate law is specifically because it tells us how the concentration changes with time. So we might have the concentration of some species A, and then in a different color, we can have the concentration of some species B. And this is similar to what we saw before. A is going to be changing and B is going to be changing like this. The rate law is going to specifically tell us the mathematical form of this graph. How does it do that? The way that it works is we write down the rate law and then recognize that the rate itself is going to be a derivative of a concentration. And so we've already seen that expression before. This is a type of equation here called a differential equation. And differential equations are mathematical concepts that you would cover once you finished calculus. And I don't think anyone in this class has taken differential equations. I could be wrong, but differential equations tend to be very useful for describing physical processes and physical phenomena. It's like, it's really what puts to work all the techniques you learned in calculus to solve real physical and chemistry problems. So obviously this is not a differential equations class, so I'm just going to tell you the solutions to the differential equations, because in the end, what we get from the differential equation are these functions here in this plot to the left. So for a rate law of the sort that I have written up there, it turns out that the concentration of A at any given time is equal to the starting concentration of A, which remember is this point right up here, multiplied times E raised to the power of that rate constant times time. Okay? Next, we can also use the differential equation to find how the concentration of B changes. It equals the starting concentration of A minus the starting concentration of A times e to the negative kt, like so. And these two equations tell us the functions of these different curves up here. All right, so as these curves are changing with time, we can just look at these mathematical forms and see how they're changing. These equations only apply to the sort of first order reaction that I'm depicting here. And one of the most common types of first order reactions we encounter is that of nuclear decay. So an example might be we have a nucleus of uranium-238 and it decays to krypton and barium, for instance. This happens to be an example of a first order reaction. It's not a chemical reaction, it's a nuclear reaction, but kinetics can describe nuclear reactions as well as chemical reactions and lots of other things besides. Now, you may have heard of this concept before, the so-called half-life. Clearly, radioactive substances have a half-life. You've probably heard of that before. Other things have a half-life. For instance, the half-life of caffeine in your body as it metabolizes it. So let's take a look at what the half-life means. So I'm going to write down the reaction, the concentration as a function of time that I put on the last slide. Okay? Now the half-life is the time it takes for half of the reactant to disappear. And the way that we solve for that is we will set the desired concentration to 1/2 of the starting concentration. So if we set A to 1/2 A0, then that's going to allow us to solve for the time that it takes to get half of that reactant. So we get 1/2 concentration of A starting equals concentration of A starting e to the negative kt. Those cancel out. So then, and then once those cancel out, we can take the log of both sides, and we get the log of 1/2 equals negative kt. And then when we solve for t, that t is going to equal negative log 1/2 divided by k. And this is often indicated as T1/2 for the T half-life. We can use the same technique to determine, okay, how much time does it take to lose 80% of our reactant? The way that we would do that is we would say that the concentration of our reactant, if 80% is gone, then only 20% remains, which is 0.2 times whatever the starting concentration was. So if you were trying to solve a different sort of problem, not half-life, but how much time it takes for 80% to disappear, or some other arbitrary number, then you would just plug this number in there instead, and it would go right up in there. And then you would just perform this same procedure.